Alright, in this video I'm going to teach you how to use the properties of exponents. So first of all, if you look on the left here, it says Exponent Rules. And actually these rules, if you look at the proofs of these properties of logarithms, these rules of exponents are what justify those proofs, or they're a main part of the proofs. And the other thing that you'll see if you look at the proofs of these is you've got to, at some point, go from exponential form to logarithmic form and then usually go back. So let's go ahead and, in this video I'm just going to be using the properties, but if you look at those proofs, they're kind of neat proofs and pretty simple to follow. I will do the change of base rule, or show you how we get the change of base rule, which is the last rule we'll cover in this lesson. So let's go ahead and get started. The properties of logs, the first one is what we call the product rule. Notice the product of the log of a product, m times n, is equal to a sum of logs. So we get addition of two logs. And the next one is the quotient rule. And we're going to call this property 2, product rule property 1. So notice here the log of a quotient, m divided n, is equal to a difference in logs. And then the last one here, the power rule. Notice the log of m to some power is equal to that power times the logarithm. So basically we move the p off the m and it goes out front. So these are our three rules or properties of logarithms that we're going to use as we expand and condense expressions, which is what we'll be doing here. So on number 1 here it says expand each logarithmic expression, evaluate logarithmic expressions where possible. Alright, so if you look at the first one, we're going to be using the property 1 because we have the log of a product. We're going to use the product rule. So here our m is 9 and our n is x. And so this would equal the log of 9 base 9 plus the log base 9 of x. And now if you look at this a little bit carefully, look at the log on the left. Remember, a logarithm represents an exponent, and in this case we can evaluate this one. We're looking for, so basically again, a logarithm's an exponent. So in this case it's the exponent you put on a base of 9 to get 9. And so that would be 1. So we're going to get 1 plus log base 9 of x. Alright, so number 2 works similar. If you want to try it, you can, and then you can watch the video. Alright, so again we're going to use the first property because we have the log of a product. So we can break that into a sum of logs, the log of 100 plus the log of x. Notice our base here is 10. Since it's not written, it's understood. These are what we call common logs. And again, we've got similar situation to example 1. The log of 100, again, our base is 10 there. So in this logarithm, the question is, what exponent do you put on a base of 10 to get 100? And that would be 2. So we're going to get 2 plus log of x. Notice on example 3 we have the log of a quotient. So we're going to use the quotient rule, and we can write this as a subtraction of 2 logs. The log base 5 of 5 minus the log base 5 of x. And again, if you look on the left, log base 5 of 5, we're looking for the exponent that you put on a 5, a base of 5 to get 5. Well, 5 to the first power would be 5, and so this is 1 minus the log base 5 of x. And by the way, if you're having any problems evaluating the logs, like log base 5 of 5, you can watch the video that I'm doing on logarithms. So if it's not up, it'll be up soon. All right, example 4. Again, we have the log of a quotient. This is going to be property 2. So the log of x minus the log of 1,000. And again, this is a base 10 log, the second log here. And so we have to ask ourselves, what exponent do we put on a base of 10 to get 1,000? And that would be 3. So we can write this as log of x minus 3. All right, number 5. So notice here we have we're going to end up using our third property, the power rule, because we have a power of x. The log base b of x to the 7th power. So we can move that 7 out front, and that's all we have to do here. And the same thing on number 6. We're going to use property 3. We can pull that 8 out front. Let's look at example 7. On example 7, when we look at our properties of logs, we don't have anything in terms of radicals. But if we think back to radicals, we know that we can write those using fractions as exponents. So this is really the natural log of x to the 1/3 power. Remember, this number here is your root. So now we can use our third rule, the power rule, and we're going to get 1/3 the natural log of x. Now let's look at number 8. Now we've got a product, x times y cubed, and we've got a power, y cubed. Now the 3 only applies to the y, not the x, just the y. And so the question is, which property do I use first? I'm either going to use the power rule or the product rule. Does it even matter which one I use first? Well, let's look at the power rule. With the power rule, notice it's m to the p power, so there's just a single value m as a base. And so in this problem, that x is kind of an extra number. We can't use the power rule here, but we can use the product rule, so let's go ahead and do that. Whoops. All right, so we're going to use the first property, the product rule. So we can write this as a sum of logs, log base b of x plus the log base b of y cubed. And then you'll notice we have the y cubed there, so now we can move that 3 using the power rule. So we're going to get the log base b of x plus 3 times the log base b of y. All right, let's move on to number 9. So similar to number 8, if you look at that e to the 4th, if it wasn't for the denominator of 8, we can use the power rule here. But the 8 is there, so we don't have just a single base to a power. We can't use the power rule yet, but we can use the quotient rule, so let's go ahead and do that. So it's the natural log of e to the 4th minus the natural log of 8. And here we do have a power that we can, that 4 there, we can move that. So let's do that next using the power rule. So we get 4 times the natural log of e minus the natural log of 8. Now if you look at the natural log of e, well, we know that natural logs are base e, so this is one of those that we should be able to evaluate. So let's look at this. Again, our base is e. So the question is, again, this is an exponent. That's what a logarithm represents. It's the exponent you put on a base of e to get e. Well, that would be 1. So this becomes 4 times 1, or just 4, minus the natural log of 8. All right, let's move to example 10. So again, it looks like we're going to be needing the quotient rule, but we do need to take care of that square root first. Notice we could write that as x plus 1 to the 1/2 power. So I'm going to go ahead and use the quotient rule, but I'm going to rewrite that with it as x plus 1 to the 1/2 power. So again, we're using the quotient rule. So log base 5 of x plus 1 to the 1/2 power minus log base 5 of 25. And now we can move that 1/2 out front using the power rule. And let's do that. And notice the log base 5 of 25, well, again, this is one it looks like we could evaluate it. We're looking for the exponent you put on a 5, a base of 5, to get 25. Well, 5 squared is 25, so this is just minus 2. All right, let's look at number 11. So you'll notice we've got a product in the numerator there. We've got a quotient because of the fraction, and we have 2 powers. And so we're going to use all 3 of our rules. And again, the product rule, we can't use that because we have a denominator here. We can't just pretend that's not there. We can't use the power rule because we don't have a single base to a power. So quotient rule is the only thing we've got here. So let's go ahead and use that and write this as a subtraction of 2 logs. And then if you look at log base b of x times y cubed, that's a product, and so we can break that into 2 using the product rule, or I'm sorry, yeah, the product rule. And so I did that, and then don't forget to rewrite the minus log base b of z squared. And then now we can move those powers. We'll use the power rule. We're going to get log base b of x plus 3 log base b of y minus 2 log base b of z. Notice when you're expanding, which is what we're doing with all these problems, we end up with logs of a single value, the log of x, the log of y, the log of z here. And that's what we're looking to do when we expand a single logarithmic expression. Okay, number 12. Now, you might be tempted to use the quotient rule here, but we can't just pretend that radical's not there. The fraction's under the radical. We need to deal with that radical first before we can use the quotient rule. So we know that a square root is basically something written to the 1/2 power. So let's go ahead and do that first. We'll just rewrite this. And now we can move that 1/2 out front using the power rule. So let's do that. And now if you look inside the parentheses there, we have a quotient. So now we're going to use the quotient rule. And so we're going to get 1/2 times the log base 3 of xy squared minus log base 3 of 13. Now notice I use parentheses because I'm replacing 1 log with 2, and the 1/2 is multiplied times that log. So if I replace it with 2 logs, it's going to be 1/2 times the 2 logs. Now let's go ahead and do the product rule next, because we do have the log base 3 of x times y squared. Let's do that. So we're going to use the product rule, rule 1. And so we'll get the log base 3 of x plus the log base 3 of y squared minus the log of 13, all multiplied by 1/2. And we've got the y squared. We need to take care of that. So let's go ahead and use our power rule. So I just moved the 2 out front. And so now I'm going to go ahead and distribute the 1/2. Now keep in mind you didn't have to do it exactly in this order. You could have distributed the 1/2 earlier. I just tried to keep it as simple as I could. So we're going to get 1/2 the log base 3 of x. And then 1/2 times 2, that's going to be 1. So it'll be plus the log base 3 of y. And then 1/2 times a minus log of 13. That'll be minus 1/2 times the log of 13. All right, let's move on. So now we're going to go the other direction, and we're going to condense logs. Now you might be wondering why we're going through all the trouble of doing this. One of the reasons why is, particularly in a course like calculus, sometimes we do 2 major things in calculus. We evaluate derivatives, and the other would be integrals. And sometimes one form of a logarithm is easier to work with than another. So that's one place where we do this kind of thing. We're going to be doing it when we solve equations. In particular, if we have 2 logs, we'll combine those into 1. And so what we're about to do is more like what we're going to be doing when we're solving equations when we get to the next chapter, or the next section. All right, let's go ahead and do number 13 here. I'm going to go ahead and write the log, our properties at the top here so we have them. So we got the product rule, the quotient rule, and the power rule. So notice here we have a sum of logs, and so we can write this as the log of a single product. This would definitely be rule 1 since we have a sum of logs. So it'll be the natural log of x times 3. We normally put the 3 first, so this is natural log of 3x. And on 14, notice we have a subtraction of 2 logs. So we're going to use the quotient rule. Again, we're doing what we did earlier, but we're going in the reverse direction. So now we can write this as the log of a quotient. The log of x divide 3x plus 7. It is important that you do put the x in the numerator and the 3x plus 7 in the denominator. Order does matter with these. Let's look at example 15. Now, you might be tempted to go ahead and use the product rule, but if you look at the product rule, particularly right here in the front, in both cases, the log has no number in front of it. And so in number 15, you have 5 times the log base b of x and 6 times the log base b of y. We can't use the product rule because we don't have 1s in front of the logs. They're not in that form, the form that the product rule is in. So, but look what I can do. I can move that 5 to become an exponent using property 3. So basically, we're going to move this 5 to here and this 6 to here. And again, we're doing the power rule in reverse. So let's go ahead and do that. We get the log base 5 of x to the 5th plus the log base the log base b of y to the 6th. And now we do have the right form to use the product rule. So let's do that. We're going to get the log base b of x to the 5th times y to the 6th. All right, you might want to try the next two and then play the video. I'm going to go ahead and do them. All right, so we have a quotient here, but we can't use the quotient. Just like on number 15, we got the 2 in front of our log, and we got the minus 1/2 in front of our log. And so let's use property 3 to get those numbers moved to be exponents. So again, I just moved the 2 here and the 1/2 here. And so now we can use the quotient rule. And you'll notice also I changed the y to the 1/2 power to the square root of y. Actually, that's what I did, and now I'll use the quotient rule. So we'll get the natural log of x squared over the square root of y. And let's look at number 17. So again, we're going to want to use property 3 first and move the 4 and the 7 here and also the 3 using the power rule. Notice I don't want to mess with the sign there. I don't want to use -3. I just want to put a 3 there. So we're going to get the natural log of x to the 4th plus the natural log of y to the 7th minus the natural log of z cubed. So now, if you look at the first two logs here, I can use the product rule. And let's go ahead and do that. So we can write that as the natural log of x to the 4th times y to the 7th. And now I have a subtraction of 2 logs, so I can use the quotient rule. And so we're going to get natural log of x to the 4th times y to the 7th over z cubed. So I want to point something out to you here. There's a pattern, and if you notice this pattern, it'll make it easier when you're doing these logs. So notice here you have a positive first term, and that x to the 4th ends up in the numerator. You have a positive, it ends up being natural log of y to the 7th, and that y to the 7th ends up in the numerator. Where you have the minus here, we have minus the natural log of z cubed. that z cubed ends up in the denominator. So that's something to watch for. In fact, after you've done a few of these, you may be able to go directly from here to here, or at least from here to here. All right, let's move on. All right, so on number 18, I think the first thing I'd want to do is distribute that 1/2. That's about all we can do at this point. All right, and so actually I'm thinking about this. We could probably do it either way here. I'm going to do it. That's all right. We'll go this way. We actually could use the quotient rule first. You'll end up getting the same answer. I don't know which one's better. Kind of probably a personal choice. But anyway, let's go ahead and now move those. We can use property 3 and move those 1/2s to be exponents using the power rule. And so now we can use the quotient rule. And also remember, anything to the 1/2 power is a square root. So I'm going to go ahead and take care of that too. So let's use the quotient rule. I said that wrong. So we're using the quotient rule. We already used the power rule. And so now we can write this as a single, the log of a single radical, the square root of x over y. All right, let's move on to number 19. So we can start the same way, well, except for here we don't have to worry about distributing. Let's move the 1/3 and the 3 using our power rule. So we get log base b of 27 to the 1/3 power minus log base b of 5 cubed plus log base b of 4. Now keep in mind, 27 to the 1/3 power, that's the cube root of 27, which is 3. So we can rewrite, and the other thing you'll notice is 5 cubed we could write as 125. So this is log base 3 minus log base b of 3 minus the log base b of 125 plus the log base b of 4. Let's go ahead and use the quotient rule for the first two there. We get a log base b of 3 over 125 plus log base b of 4, and then now we can use the product rule and we'll multiply those two together. And 3 times 4 over 1, or it's 3 over 125 times 4 over 1. We're going to multiply the 3 and the 4, and 125 would be times 1. You're just going to end up with the log base b of 12 over 125. All right, let's look at the change of base formula. So first of all, this is actually the proof of it. It's kind of a nice proof, and it's similar to the kinds of proofs you'll see if you actually look at the proofs for those 3 properties, the power rule, the product rule, and quotient rule. So notice, first of all, we start by letting x equal log base b of m. And going from here to here, all I'm doing is changing forms from exponent or logarithmic form to exponential form. And then I took the log base 10 of both sides here, and then notice I used the power rule to move that x out front in here on the left side there. So now at this point we're trying to get x by itself, so we can divide each side by log base b, or the log of b, I should say, the common log of b. And so you can see that we end up with x equals the log of m over the log of b. So that what that really is saying, well, actually, let me finish the proof. We said x was log base b of m, and so we have the proof. Whoops, hold on a second here. Getting ahead of myself. So if you go back up here, what this is saying is if I start with some base, here it's b, I can rewrite this as a difference of, or a quotient of 2 logs, where we're going to change the base to a base that we have on our calculator, base 10. So it becomes the common log of m divided by the common log of b. The way I remember it is the m is higher than the b on the left side, and so when you rewrite it, that's the case as well. So anyway, it's a nice rule to help us evaluate logs that we couldn't evaluate before. So if you look at number 1, the question will be, what exponent do you put on a base of 3 to get 8? And there's no nice number that would work. But we can use the change of base formula and write this as the log of 8 over the log of 3. Now again, these are common logs, base 10. And now when you put that into your calculator, you'll get 1.893 if we round to 3 decimal places. Now remember, this is the exponent that we put on a base of 3 to get 8. We can actually check this by putting this exponent or this number on the base of 3, and if you check that, you do get about 8. Since we're rounding here, it won't be exact, but it'll be very close. So on number 2, you can write this as the log of 5 over the log of 2. And if you put that in your calculator, you'll get 2.322. And again, you can check that. If you put it into your calculator, 2 to the 2.322 power is about 5. And the only other thing I would mention is if you have a TI-84 and you look in the math menu and you find the formula that has the logarithm in it, some do, some don't, you can actually evaluate these without the change of base formula, and that's fine. But for those that don't have that function, this is what we use. All right, and that's going to be it for this video.